In this video, I'm going to provide a solution to question 5 from the Matrices exercise level 2. And if you've not done this question, please, this is the first part, so I suggest you pause the video now and try this before we look at the solution. Okay, so it wants the values of k for which the matrix A is singular. Well, we know that a matrix A is singular if and only if the determinant of A is equal to 0. So we need to calculate the determinant of A. Well, looking at this, we want to we can take any row or column to calculate the determinant, but actually the middle row seems to be a sensible choice because it's got a 0 and 2 ones in it. So what is the determinant of A? Well, it is equal to this element here, 0, multiplied by the determinant of those remaining elements. But actually we need to be a little bit careful here because we remember our matrix of signs. This cofactor comes with a negative. Then we have the second element here, the 1, which has a positive sign, multiplied by the determinant 2 minus 1 minus 3k. Then finally our third cofactor is 1 with a negative sign, multiplied by the determinant 2, 0 minus 3, 2. And this is singular if and only if this is equal to 0. So what do we get if we expand this determinant? Well, we get 0 times k, subtract 2 times negative 1, well, and that's also be multiplied by 0, so it doesn't really matter what that is. We get 1 lot of 2 times k, subtract negative 1 times negative 3, which is negative 3, and we get negative 1 lot of 2 times 2, which is 4, subtract 3 times 0, which is 0, so we get 2k, subtract 7, which is the determinant of A, is equal to 0. So what is k when A is singular? Well, k is equal to 7 over 2, or 3.5. Okay, part 2 of this question asks you to find A inverse when k equals 3. And again, if you've not done this, please pause the video first and try this yourself. Okay, well, you might want to just substitute k equals 3 straight into the matrix. I'm not going to do that. I'm going to find A in terms of k and then substitute k equals 3 in, because that's a skill you need to have. So, what do we know about finding the inverse matrix? Well, we know that A inverse is equal to 1 over the determinant of A. And then we need to start finding our cofactors. So our first cofactor comes from the element 2 here, and that is going to be 1, 1, 2k. Our second cofactor comes from the element 0 here, so that is going to be 0, 1, minus 3k. And our third cofactor comes from the element negative 1 here, so that is 0, 1, minus 3, 2. Okay, the second row, if we take our element 0 here, we have the cofactor 0, negative 1, 2k. If we take our 1 here, we have the determinant of 2, negative 1, negative 3k. And if we take our final element 1 in that row here, we have the determinant of 2, 0, minus 3, 2. And then if we go for the final row and our element negative 3 here, we have the determinant 0, negative 1, 1, 1. Our 2 here gives us the determinant 2, negative 1, 0, 1. And finally, the element k gives us the determinant of 2, 0, 0, 1. We need to be a bit careful because firstly, we remember we're going to transpose this. So this t tail is going to transpose. And actually, these aren't our cofactors at the moment. These are just the minors. We need to make sure they have the correct sign according to our matrix of signs. So let's put in the appropriate negative signs. And this is our inverse matrix A. So all it takes now is we need to calculate this. Well, the determinant of A, actually we found this before. The determinant of A is 2k minus 7. So we know this is 1 over 2k minus 7. And now we're just going to calculate these determinants and then transpose. So the first one is 1 times k minus 2 times 1. So there's k minus 2. The next one is 0 times k, which is 0. Subtract 1 times negative 3, which is positive 3. Then multiply that by negative 1, which gives us negative 3. And 0 times, in the next element, is 0 times 2. Subtract negative 1 times 3, which is 3. The element below, we get 0 times k times, subtract negative 1 times 2, which is positive 2, but we have our negative sign, so that is negative. The next one, we get 2k plus 3. Sorry, 2k subtract 3. Here we get 2 times 2, which is negative 4. Here we get 1. Here we get negative 2. And here we get 2. Okay, and now all we need to do is transpose this. So we get 1 over 2k minus 7. K minus 2, negative 3. 3 in the first column. Negative 2, 2k minus 3. Minus 4 in the next column. And 1, negative 2, 2 in the final column. And then we're just a matter of substituting k equals 3 in. So if we substitute k equals 3 in, this becomes 1 over negative 1. So negative 3 minus 2 is 1. Negative 2, 1. Negative 3. 2k subtract 3 is 3. Negative 2, 3. Negative 4, 2. And you may want to bring that negative sign inside the matrix and change the sign of all of those elements. Okay, part 3 asks if k equals 3.5 and a multiplied by the vector xyz is equal to 4, 3m, give the value of m that means that there is a solution. Interpret this geometrically. So again, if you've not done this, pause the video now and try this yourself first. Okay, so what do we know? Well, we know that xyz is equal to a inverse of 4, 3m if a inverse exists. And if a inverse does exist, there will be a unique solution. So in terms geometrically, this will be a point in 3D space. However, let's have a think about this because we know k equals 3.5 and we knew about the determinant of a from above. We knew that the determinant of a was equal to 2k minus 7. And we knew that exactly k equals 3.5 was when a was singular. So this is exactly when a inverse does not exist. So we know here there is not a unique solution to these set of equations. However, let's write these out as some simultaneous equations. So if we multiply the matrix A, so if we multiply that by x, y, z, we get 2x minus z equals 4. We get y plus z equals 3, and we get minus 3x plus 2y plus 3.5z equals m. And we know there's not a unique solution to this, because we've already shown that a is singular. But we also should notice that this plane 1 has a normal 2, 0, 1. Plane 2 has a normal 0, 1, 1. And plane 3 has a normal minus 3, 2, 3.5. So if you think carefully, none of these planes are parallel because they all have different normals. So no parallel planes. So what does this leave us? It leaves us in this situation with two possibilities. Either these, so we've got three non-parallel planes, so either these three planes form a triangular prism, or actually they coincide along here, along a line. And this just depends on the value of m, because they always have the same normal. If you start to vary m, all that happens is the planes move up and down without changing their angle. And I've made an example here to show this with a slightly simpler, so these aren't the same planes, but we can see that we have three planes with three different normals, and as we change the constant, the normals of those planes do not change, but one of the plane's positions do. So at the moment they're forming a triangular prism, but there's one particular point, one particular constant where all three planes meet at a line, which we can see is about now. So in our particular case, we want to find the time when these planes, the value of m for which these planes meet along a line, and we might call this a pencil or a sheaf. Okay, so what needs to be true for these planes to meet along a line? Well, what we need to have is we need to have the equations 1, 2, and 3 being consistent. And normally we'd do this by creating two equations in two variables and making sure those equations essentially told us the same information. But it's slightly simpler here because we notice equation 1 only has the variables x and z in it, and equation 2 only has the variables y and z in it. So it doesn't really matter which of these we start with. You might want to try this by fixing equation 2. I'm just going to stick with equation 1, which is 2x minus z equals 4, which is equation 1, and then I'm going to take equation 2 and 3, and the variable I no longer I've eliminated is y, so we're going to eliminate y from equations 2 and 3. Well, I can do this by doing equation 3 subtract 2 lots of equation 2, and this will give me negative 3x. 2y subtract 2y is 0, which is exactly what we wanted, and then we have 3.5z minus 2z, which is plus 1.5z, is equal to m subtract 2 times 3, which is 6. Let's call this equation 4. Well, if these two equations are consistent, equation 1 and equation 4, then we're going to have this situation. If they are inconsistent, we will have this situation where we have a triangular prism in 3D space. Well, notice that the x and z's in equation 1 and equation 4 are in the same ratio. So for these to be consistent, they essentially need to tell us the same thing. Well, what might be a nice way to do this? There's lots of different ways of doing this, but I'm going to take equation 4 and I'm going to divide throughout by negative 1.5. So I get negative 3x over negative 1.5 plus 1.5z over negative 1.5 equals m minus 6 divided by negative 1.5. And we can see that this is saying 2x minus z equals m minus 6 over negative 1.5. Well, for equation 4 and equation 1 to be consistent, we've got 2x minus z is 4, and 2x minus z is m minus 6 over minus 1.5. So it must be that m minus 6 divided by negative 1.5 equals 4. Then solving this equation for m, we have m subtract 6 is negative 6. Adding 6 to both sides, we have m equals 0. So the value of m, which makes these equations consistent, is m equals 0, and that is the case where all of the three planes intersect along a line. So we actually have an infinite number of solutions that form a straight line in 3D space.